So, lecture number 12, 2D raycasting and line segment intersection. So this is not necessarily a game programming topic, but it is a mathematics topic that is going to be very, very useful when we try and program many different features in our games, especially 2D games. And just keep in mind that we are making a 2D game engine for this course. And so if you were doing a 3D game engine, there are functions and mathematics just like this, but except in 3 dimensions. So I'm sparing you the 3-dimensional version for this particular course, but just realize that if you're doing a 3D game, the same sort of thing exists. So, what is raycasting? Raycasting is a name for a technique which has many different applications in games, and we'll see just a few of those today. So if you've ever heard of ray tracing before, which I'm sure you all have, like all the NVIDIA RTX stuff that's going on with ray tracing. So ray tracing is essentially iterative raycasting. So a raycast is a single line segment, as we'll see in a bit, and ray tracing is multiple line segments that bounce off of multiple things. So intuitively in 3D, what we're trying to solve by doing this mathematical problem of raycasting or ray tracing is saying something like, cast rays outward from my eyes to the world, and what do they hit? Okay, so what can I see? Or similarly, how does light bounce around and stuff like that? So it's very heavy on vector math, especially once you get into 3D representations, but it has many, many useful applications. So here are some diagrams that sort of give you like the difference between ray casting and ray tracing. So over here, if we're looking at the 3-dimensional problem, a ray cast might be something like, okay, here's the camera, or here's my eye. And so if it's a camera, this is an image. If it's my eye, then it might be a plane that I'm looking through, or maybe we're talking about the computer screen into the game world, what we can see. And so we're casting rays and we're seeing, okay, what do those rays hit? What do they bounce off of? Where's the light source? And if we take ray tracing, then, you know, there could be reflective surfaces in the game. And so we wouldn't, instead of just doing one ray, we would do multiple rays. So it might bounce off of that mirror, hit that car, then hit the sun or something like that. So raycasting, essentially, for this lecture, at least in 2 dimensions, is going to be the following problem. So we're going to draw a line segment between 2 points, and so in this class, we're going to be talking about line segments, or in this lecture. So a line is an infinitely long thing. It has no endpoints. A line segment is the technical term for a line that has 2 endpoints, okay? So in this lecture, if you hear me say line, then I'm talking about a line segment, technically. It's easier to say. So we're talking about finite length line segments in this lecture. So we're going to draw a line segment between 2 points, and we're going to detect if and where a collision occurs. So ray tracing is sort of where did it bounce to, right? So where did it bounce? Where did it intersect? If no collision occurs on a line between 2 points, then they can see each other. So you may be familiar with like military terminology or video game terminology where they're talking about line of sight. And that's literally what it means, is that can you draw a single line from your eyeball or the camera or the video game monitor, whatever, can you draw a single line from your eyeball to the target? If you can, then there is a line of sight, meaning that you can see those things. Now, of course, you know, if you have mirrors set up and all that kind of stuff, you might be able to see it if there's no direct line. Maybe you bounce off the mirror or whatever, but we're not talking about that right now. We're just saying if there is no collision for that line segment from your eye to the target, then they can see each other. And so 2D raycasting, the mathematical problem of 2D raycasting, the point of doing 2D raycasting typically solves problems that deal with either light or visibility. They could also do things like, so for example, if you have a bullet that is like a hit scan bullet, meaning it travels instantaneously in a video game, then the visibility problem is also the hit scan, did it hit something problem, right? So if the bullet is the ray or the line that you're casting, if it intersects with somebody's head, then it's a headshot. If it intersects with the arm, then it's a body shot, right? So visibility is not only meaning can I see the thing, but in some cases where you have like instantaneously traveling things in a game, like a bullet in a hit scan, FPS or something like that, then that sort of did it hit the thing is the same calculation. Okay, so visibility also means did it hit the thing. But of course, if you have a bullet that has a travel time, right, a projectile, then it's not the same calculation. But for hit scan stuff, it's the same calculation. So 2D raycasting can be used for things like lighting, right? So for example, over here on the left, let's say that we have this light source in the middle of a room. And what we want to do is we want to calculate where in the room the light source hits and where in the room the light source doesn't hit. So for example here, it hits all of this area here that's in yellow. But if we have some objects here that light cannot pass through, then the spots behind those areas are not going to be lit up. Maybe there's a shadow there, right? And so we can do all sorts of cool stuff with this, like put extra graphics or shaders on top of it and make our scene look really nice. But the basic mathematics behind it is this raycasting technology. So there's a really nice article here by Red Blob Games that talks about 2D raycasting and visibility. I may show that at the end once I've talked about the mathematics a little bit, but that shows you really what the motivation for this is. And I'll also be going over another article which shows you intuitively what the calculations are to do something like this, like where are the shadows, where is the light, that sort of thing. So a really cool example of this in video games that I've seen is this game called Third Eye Crime by Moonshot Games. So in Third Eye Crime, you play this sort of detective character, and the detective, so sorry, I can't remember if you're a detective or if you're a thief, but you're trying to get, maybe you're a thief, you're trying to steal stuff, for example, maybe this diamond here, and there are guards patrolling. And those guards that are patrolling can see a particular area of the environment, right? And so, for example, here you see those cones coming out. That is the line of sight of the guards. And so the whole point is that you're trying to avoid the line of sight of the guards and collect the diamonds or whatever. So this is almost exactly the problem. This is like the problem that we will be solving in class today. How could you do something like this? I created this small demo here, which is very similar to what we're going to be seeing later. And by the end of this class, you will know how to do this. So this is pretty cool, right? So you can see here that I'm moving around this like fake light source. It is sort of brightening some areas of the environment, and where there are objects occluding that light source, it's in darkness behind that. And so it's a really cool effect, and it's surprisingly simple to do. So let's talk about that. So the very, very basics of raycasting. So the problem of raycasting basically asks, is anything blocking the path between these 2 points? Right? So I have a point over here, call it P1, and I have a point over here. So for example, is anything blocking the path between these two? In some cases it might not be. In this case, there is a line between them, right? So how would we detect this mathematically? So the path between 2 points is blocked if the line segment between them intersects with another existing line segment. So, for example, if we draw a straight line segment between P1 and P2, and this intersects with another line segment, then it is blocked, right? There is no line of sight between those two things. So that's the line segment intersection problem. But we may not just want to ask if a block exists, but where that block exists, okay? So depending on the application, we may also want to know where the first intersection is. So for example, if we are at P1 and we're trying to do like a light source, like a light calculation, right? And we want to know how far does this light go, we may want to ask not necessarily is there a block, but where's the first block, right? So we would want to know where this is right here. So there might be multiple intersections, but we want to know where that first one is. So that's the problem that we're going to be looking at today. So far in this course, we've been using the vec2 class to represent points in 2D space as a 2D vector with x and y, right? So a line segment, this is really convenient for us for this particular lecture, because a line segment can be defined by the start and end point of a line using vec2s, okay? So if I have a point A, that's a vec2 variable A with some x and y, and I have a variable B, which is another vec2 with some x and y, then I can say that this is line segment AB, okay? It's because it goes from point A to point B. So let's look at another example of this, okay? Now keep in mind for SFML, the y-axis is flipped, but for standard math Cartesian coordinates, it's 0 zeros in the bottom left. But the math will still work even if the y values are flipped. Okay, so let's say we have points A and point B, and both of these are stored as vec2s. This line segment, we're going to call that line segment AB. And now let's play around with the math a little bit and see what we can find out. So let's try some vector subtraction, okay? So if we take R, which is equal to B minus A, right? We've seen this before. We know this. We're taking destination minus source. So R represents the line segment or the vector which goes from A to B, all right? So B is going to be A plus R. And we already know this. This is pretty basic vector math. But let's introduce another concept now called a scalar. We've kind of talked about this before. But we're going to scale R by a scalar value. So that's why it's called a scalar, because you get to scale something. So right here, if I take R, like as just R, then that's 1 times R. Our scale value is 1. Right? So that's not very interesting. That's just R. So let's change our scalar value and see what happens to our vector. So for example, if we multiply R instead of by 1 by 0.5, then here's what we get. We get this line segment or this vector that goes from A halfway to B. Right? So we essentially multiply the X and we multiply the Y of R by 0.5 and we get this. So if we are at A and we multiply R by a scalar that's between 0 and 1, then we will get a destination somewhere between A and B. But if we multiply it by a scalar that's greater than 1, we will get a vector that lands beyond B. Okay? And that's going to come later. So we're going to call our scale T. So R is the vector, T is the scale value, okay? So here, this would be T times R, and the particular value of T in this example is 0.5, all right? So in this case, we have A and we have B, and we have R is equal to B minus A, and so we have B is equal to A plus T times R when T is equal to 1. Right? Because B is equal to A plus R. So down here, A plus T times R, well, this is satisfied when T is equal to 1. That's it. So it's pretty basic, but we will see where this is going to be able to take us. So, line segments. Let's add another line, because we're going to be talking about line segment intersection, and we have to have 2 lines in order for that to happen. So let's add another line. So currently we've been talking about A and B, and R is the vector between them, and T is the scalar for R. We're going to have a lot of letters, but they're going to be consistent, so it shouldn't be too bad. Now, let's add points C and point D, right? So if we're taking D as our destination, then S is going to be D minus C. So we had R going from A to B, now we have S going from C to D. All right? And U is going to be the scalar value for S. So scale S by a scalar U. And a really cool thing here is going to take place. When R and S have the correct lengths, the segments intersect. Okay? And we'll show an example of that. So if we want to do line segment intersection, then what we have to do is find the correct scale values for R and S. So we have to find the correct U value and the correct T value such that the following things happens. So in this example here, if I take T and U to both be 0.5, then you'll see that both of these vectors point to the same location, right? So they'll both meet at the exact same point. So that's what we're going to be trying to do. This is how we are going to calculate line segment intersection. If we can find the scalar values for U and T that make S and R point to the exact same spot, so they meet in the environment, then that is where our line segments intersect. See that? So here we would have values of 1 for U and T, right? Because they go all the way to their respective points. But here we have some scaled values which makes them meet in the middle. And if two line segments intersect, you can tell that there will be a U and a T where that happens. So let's look at a little bit of math here. So we've got B is equal to A plus T times R, and D is equal to C plus U times S. Right? We've already said that. So the line segments are going to intersect when these values of B and D are equal. Right? So when we have the correct scalar values, B and D will be equal. So if we want to find where B and D are equal, then we'll assume that they're equal, and we'll take this value and set it equal to this value, right? Really simple derivation of stuff. So we have A plus T times R is equal to C plus U times S. And this is what we had on this slide. A plus T times R is equal to right here, and that's equal to C plus U times S, which is equal to that same spot. So we want to find these values of T and U. So this is what this formula is going to do for us, right? So the lines intersect if both T and U are between 0 and 1. Now, what does that mean? Well, if we look back here at our example, okay, if T is between 0 and 1, then this point lies between A and B. If T is greater than 1, then the point lies outside here. And if it's less than 0, then we actually have a vector pointing in the opposite direction, which is outside of A. So in order for there to be a line segment intersection, it has to be between this A and B, meaning that T and U both have to be between 0 and 1. Otherwise, the intersection would occur outside of the line segment, which makes absolutely no sense. Okay? So that's what that thing says. So the lines intersect if both T and U are between 0 and 1. So let's have a look. We're going to set A plus T times R equal to C times U, C plus U times S. But as all of mathematics has told us for the history of time, in order to solve an equation, we need to have at least one more equation than we have unknowns, right? But here we have two equations and two unknowns. So how can we solve an equation when we have two equations and two unknowns? Well, luckily, we have a little trick up our sleeves, and this is something called the 2D cross product. So what in the hell is the 2D cross product? All right, so typically, the cross product is reserved for three-dimensional calculations, okay? So the cross product in three-dimensional space, so if we have a vector B and a vector A, then those two vectors define a plane in three-dimensional space. And if you take A cross B, that produces a 3D vector which is orthogonal to both A and B. And that's called the normal vector to A and B, right? So if you have a three-dimensional surface, if you want to calculate the normal vector, which is useful for all sorts of things, which we're not going to get into right now because this is not a 3D geometry class, but essentially the 3D cross product produces this vector for you, A cross B. But that sort of geometric visualization doesn't now make sense in 2D vectors because what does orthogonality mean in a two-dimensional space? But we still have a mathematical definition of a 2D cross product, which has a nice property that we can actually use to help us derive T and U. So the 2D cross product, the formula is the following. So if we have A cross B, that's equivalent to the x component of A times the y component of B minus the y component of A times the x component of B. All right, so you take the x's and the y's of each one, you flip them and you subtract them. That's what it is. And this is going to produce a scalar value. It's going to produce a floating point value, right? And the really cool property that this has is that any vector cross itself is equal to 0. Why? Well, up here you can see that it's the x of A times the y of B minus the y of A times the x of B. But if A and B are the same, then it's x times y minus y times x of the same vector. So it's going to be 0, right? So what we can do, and the other property that the cross product has is the following, is that if we have two vectors and we add them together inside these parentheses, right? And then we cross that by s, then that is equal to the crossing of each one with s and then the addition of those. So it's kind of like multiplication. I'm not going to say it's exactly the same, but it has this property of multiplication, where if you have two things that are added inside these parentheses and you cross them with a single thing, then you can multiply it out, so it's A cross S plus R cross S. So the two properties are anything cross itself is 0, and this property right here. And now we're going to use that to help us solve for our values. So how do we solve, for example, we have T and U, so let's just solve one of them. Okay, so let's just pick T because it comes first in the alphabet. So here's our formula. We have A plus T times R plus, or is equal to C plus U times S. Now, we have two equations with two unknowns, and we're trying to help that situation. So let's just apply the cross product of S to both sides. Okay? So, if we take the left side, put it in parentheses, and then cross it with S, that is equivalent to the right-hand side, put it in parentheses, and cross it with S, right? When we're deriving stuff, we can apply the same operation to both sides, and it'll be the same. So now we do that second property, where this becomes, we expand it, so now we get this. So we have A cross S plus T times R cross S, okay? T is a scalar, so it can be pulled outside, okay? It's just a scalar value. Is equal to C cross S plus U, which can be pulled outside because it's just a scalar, times S cross S. But look at this. What do we have here now? We have an S cross S over here, and if we remember, S cross S is 0. So this term disappears because anything times 0 is 0, and so we're able to eliminate the U from our calculation. So now we have this equation with one unknown, and now we can solve for it. So let's do something cool. So we take this, and now we have this formula with no U. So what we're going to do is we're going to take, okay, we want T to be by itself. So what we're going to do is we're going to take A cross S, and we're going to move it over here so that we're just left with T and R cross S. So we have T and R cross S over here. That's equal to this C cross S minus A cross S. And now we do the same thing that we did before, where this right here is equal to this right here, right? Because it's the reverse of what we did before. Instead of expanding it, we're contracting it. So this is C minus A cross S. So T times R cross S is equal to C minus A cross S. So T is equal to C minus A cross S divided by R cross S. That's it. So that's our value of T because we know all of these values, right? We know all of these values. So that's how we're going to solve for T. Now, if we do the exact same thing, but a little bit different, we can solve for u. So here's our formula, where instead of applying the cross product of instead of applying the tongue twister, instead of applying the cross product of s to both sides, we're going to apply the cross product r to both sides, okay? And so then we have the r over here. When we expand, we get this r cross r in a similar way. This is the exact same calculation, it's just now we're eliminating t instead of u. This eliminates the t. Now we can bring this over here, and we get the same thing for u. I don't need to go through that whole derivation because it's the same thing just on the other side, right? So now here's our value for u. And so we've got a minus c cross r divided by s cross r. So we know all of these values, so now we can solve for u, and in the previous slide we solved for t. Okay. So where these two things intersect is going to be right here, and that's t is equal to this value, and u is equal to this value. Okay? So there we go. We can stop there, right? Done. However, we don't want to stop when we know the answer. We want to stop when we have an efficient answer. Okay? So this right here is not, it's still a lot of calculation. There's a lot of subtractions, multiplications. Can we simplify this a little bit? Okay? Yes, we can. So I'm going to show you the simplification. Here's another property, is that r cross s is equal to negative s cross r. And the reason for that, if you go take the original formula, you'll see that that's pretty obvious, right? Because you've got a subtraction in the middle. So if you flip them, then you'd have to put the negative outside. It's pretty easy. So if r cross s is equal to negative s cross r, then we're going to apply a pretty cool thing to the above. We can rearrange the above. So where we have, for example, a minus c cross r, we can replace the a minus c cross r with a negative c minus a cross r. So there's a negative out here right now. But over here, what we're going to do is flip this and put a negative outside. So those two negatives cancel. Okay? And now what we have is, instead of u being equal to this, we have u being equal to this. And you might say, okay, well, all you did was rearrange it. It's the same, it's the same amount of calculations. However, look at this. Now, t is equal to this, and u is equal to this. So c minus a is used twice, and r cross s is used twice. So we can compute them only once, and then use their values twice. Okay? So in the original version, we would have had to compute r cross s and s cross r, and c minus a and a minus c. But now, we have two of these values that are used twice, and only need to be calculated once. So we can compute them once, store their value, and then use them twice. Okay? So here's the whole thing kind of in a nutshell, is that if we want to find this intersection, well, what we did was we set two values equal, we found the values of t and u, and so here's the value of t, here's the value of u, and we have an intersection if t is in between 0 and 1, and u is in between 0 and 1. And once we find t, and once we find u, we can then find the intersection point very easily by just taking, okay, our intersection point is either a plus t times r, or c plus u times s, because they're both pointing to the same place, and so we only need to use one of them, right? So this is the whole thing. This is line segment intersection. You have a calculation, you have a little check here, and then you have the final calculation of the intersection point. So if you take that and you want to put it into code, which you're going to want to do probably for assignment 4, because you're going to have to do this, is we're going to do the following. So we are going to have a little struct here, and a struct is just like a class, remember? So that's going to store a Boolean result. So this result is going to be if there is an intersection. And then if there's an intersection, we're also going to store the position of that intersection, okay? So the result of our calculation of the function line intersect isn't going to be just a position, and it isn't going to be just a result. It's going to be a result and a position, okay? So here we have line intersect. It's going to take in 4 vec2s. Now this is obviously not C++ syntax, it's pseudocode, but it's going to take in these 4 points, right? And we are assuming that from those 4 points, we have a line segment AB and we have a line segment CD. So the first thing we do is we calculate R, which is just B minus A, and we can do that because our vec2 class has a really nice subtraction method. We also have vector S, right, which is equal to D minus C. We have a float because the result of a cross is the result of a 2D cross product is a scalar or a floating point value. So I'm calling this RXS, right, because it looks like it. So we compute RXS and we compute that and we store it. Next, we compute and store C minus A because we're going to use that twice, remember. Then we have a float T, that is the scalar value that we're scaling the vector from A to B, and that is equal to CMA, right, C minus A cross S divided by R cross S. And then we have U is equal to this. Then all we have to say is, okay, if T is between 0 and 1, and U is between 0 and 1, then I'm going to return true, meaning that we have an intersection, right? And the point of that intersection is, well, here's the X value and here's the Y value. That's it. We've already talked about how you do that. And if this is not true, else we return false and we don't really care what this position is because there's no intersection. Okay? So there you go. That is line segment intersection. Now I could have just given you this slide, but then you wouldn't understand, right, what's going on. And now, I mean, if this course had an exam, you'd be able to answer a question about it, but it doesn't. But that's why we do it this way. And I don't want you to just regurgitate formulas. I want you to understand what the hell is going on. All right. Now we know how to intersect lines. How can we use this for game visibility, right? So now that we know how to do line segment intersection, how can we use it for visibility? If a line segment AB does not collide with any vision blocking entities, then B is visible to A. That's it, right? So you could have multiple entities blocking vision. You could have one entity blocking vision. You could have no entities blocking vision. Now you can figure that out. However, what about non-line game objects, right? So in our game, let's say we have a point A and we want to know if it's visible to point B or not. Well, we may have like these entities out in our world that aren't just lines, right? So how can we compute the visibility if we have like arbitrary geometry things in our world? Well, it's kind of easy. They're made up of line segments, right? So all you have to do is you compute, okay, does line AB intersect with with any of these line segments? So it turns out here that if we look, AB intersects here, it intersects here, it intersects here, and it intersects here. But if we're doing something like a lighting calculation, we only want the light to go this far, right? We only want it to go right here and stop as soon as it hits this thing. So what we do, we find the places that it intersects, and we just take the closest one. That's it. Alrighty. So the entity can see up to the closest intersection. And you just take the distance between A and the intersection point, you get the distance, and then you can find the closest one. Anything beyond that is outside of its vision. So A cannot see over here, for example. So, 2D game lighting effects. Caveat, here's an important note. This is not the only way to do this, and it may not be the most efficient way to do this. There are ways of doing this that are like massively parallel. You can do them with shaders. You can do them in the GPU. There are better ways of doing this. However, this is mathematics. It's a computer science course. I am trying to teach you how to like understand the way that this works. And then later on, you can go and optimize the hell out of it and try and parallelize it and all sorts of stuff like that. We've got a really loud airplane going overhead. Not sure if you can hear that or not. So light doesn't just travel in a straight line like this. Light travels like outward in all directions, right? You shine a light bulb, it's going to go everywhere. So how do we calculate everywhere that light lands, right? So how did I make this, right? It's not just one line segment. How did I make this? Well, there are several possible solutions to this. But what I'm going to do is I'm going to go to this really cool one because it has all of the math done for you. I'm going to explain intuitively how it's done. And then for your project, you are going to have to include some sort of lighting effect. Okay? And you can use this one if you want to, or you can use any of the math on this page. I do not mind if you take their methods. I just want you to include on the project, which we'll talk about next week, one of the requirements is that you have to do a lighting effect. So if you want to do something like this, if this starts up, you can, and you'll know how to do the math of this pretty soon. All right, so let's go to this website, and I'll show you. And again, here's the website for that. I will copy and paste these links in the chat so that they are there for people who may not want to type that in. All right, so there are the two links. And here's the first one. We are going to be following this demo. And this is there for your benefit if you want to read it. And you can use that method if you want to, but we're going to be following this method just for the class. All right, so let's go over here. And I've already got this loaded up. And it's a really, really cool demo. So here, you might notice the positions of these objects are the same as in that video I showed you because I copied from this website, right? Just to show you. But it's really cool. So here's this demo. It looks kind of similar to what I did. However, they have this cool thing where if this person is like in the shadow, then a different texture gets drawn, right? But it's the exact same calculation. So how does this work? Because we talked about a single line segment, but we didn't talk about how to calculate light going in all directions. All right. Well, I'm not going to read this entire website, okay? But I am going to go through just the visuals because the visuals are really, really nicely done. So here's sort of what we talked about so far. We have an environment. Here's the environment. It has some polygons in it. They are made up of line segments. That's our environment. And this environment, okay, we're going to have a light source in it. And so where my mouse is, that is where the light source is going to be. So if I scroll down, here it talks about a bunch of the math that we just talked about, okay? But that we have already talked about that. Ours is a little bit more efficient than this, all right? So don't copy this one, copy the one from the slides. And so what that math was talking about is how you do this. So if now, instead of the mouse pointer being where the light source is, we are assuming that the light source is in the middle, and now we're drawing a line segment toward the mouse cursor, okay? So the line segment is going toward the mouse cursor. If I move the mouse around, it's finding where it intersects, okay? So we know how to do this, right? We know how to do this. We're taking a line segment from the middle out toward the edge somewhere, so some big line segment, and we are calculating where it lands. And so we would just check over all of these line segments. We'd have all the line segments stored in some data structure somewhere, and we would calculate the closest intersection. And now we also have to do the line segment, which is actually the outside of this box, right? The outside of the environment. So those are line segments as well. So that's what we're doing. So now, how would we turn this into a line, like a light source that instead of shining just on one vector, shines everywhere? Well, the first thing that you could think of is let's just shine a bunch of rays, right? So in the previous one, we had one light, like the light source was in the middle and it's just pointing toward the mouse. Now we have the light source at the mouse and it's just shining, like I think here there's 50 rays. So we have 50 rays equally radially spaced in all directions. And you can see here, oh wow, look at that. So that's kind of what's happening, right? We have 50 rays. Those rays are going outward. And you can see here, I really can't move my mouse because it'll move the light source. But like the triangle up here, if you look up here, then that place, the light is not reaching there, right? Over on the left here, the light is not reaching there because it's colliding with all these things. So this looks like the way you would do it. However, let's take that and we'll flesh it out a little bit, okay? So now what we do is we take these rays and we radially sort them, meaning we're going to sort them around in a circle, okay? So I'm going to bring up the handy dandy blackboard and talk about what I mean here. Oh, actually, let me show you one more thing first. After we sort them, we're going to turn these rays into these polygons, okay? And I'll show you how we do that. So let's look at how we create these polygons. So here's the blackboard. I'm going to have this light source here. Let me probably draw in white, I think would be best. So I'm going to have this light source here in the middle. Okay, so that's the middle. And now we're going to have a bunch of rays. So let's say this ray goes out to here. This one goes to here. This one goes to here. This one is here. This one is here. This one is here. And maybe this one is here. Okay, so these are the rays that we shined out. I know that it's not quite as nice as that website, but it's all I can do with the MS Paint blackboard. Okay, there we go. There's some other ones. Now, how do we turn these into actual polygons, right? Well, we're going to be drawing triangles. And the way we draw triangles is first, how do I know which triangle to draw? So for example, if I have, what color can I use here? I'm going to use yellow. So, oh, that's really, how do I know, for example, whether to draw this triangle or this triangle or this triangle? So what we actually want here, it's called a triangle fan. And in order to do a triangle fan, you need to sort your points in a list in order of their angle, right? So all we do is we take some arbitrary line. So for example, this line here at the x-axis, and we're going to measure between that x-axis and each line segment the angle. Okay, so we know how to calculate that angle. We've talked about that math already. And once we have the angle, we sort these lines so that they are in order of increasing angle. Then what we do is we take our triangle fan, which is a type of thing that we can do in SFML, or we can draw separate triangles if we want. And we can say, go from the first line segment to the second line segment and draw this triangle. So from the origin to the first to the second, then from the origin to the second to the third, then the origin third to fourth, origin fourth to fifth, origin fifth to sixth, sixth to seven, seven to eight, 8 to 9, 9 to 10, 10 to 11, and 11 back to 1. Okay? So that is how we turn those line segments into polygons. We first calculate the angle of all the line segments, then we sort them based on that, and then we have what we have on this website. Okay? So going from here to here is what we just did on the blackboard. Now, here is where we run into the problem. Back when we did this, we like, oh, that's super smooth. It looks like it would work, right? But when we translate it into polygons, now we can see, oh, look over here, for example. There's a little bit of clipping over the edge of that polygon, right? There's a little bit of clipping over the edge of these triangles. This one gets covered. This one gets covered. It's a really jittery effect. It's kind of like giving me a headache. That is not what we want. Okay, this is not a good light calculation. The light shouldn't go over these corners here. So what can we do then? Let me try and take a screenshot of this environment, and then I will paste this into our blackboard. All right, so let's go back to the blackboard, and I will undo what I have here, and then paste this in here. Okie doke. So what we did before was we drew a bunch of line segments in kind of just arbitrary directions, right? So we said, okay, let's draw 50 line segments, let's draw 100 line segments, let's draw 1,000 line segments, whatever. They were sort of equidistant radially from the center. So we might have had one here like this, we might have had one here like this, and we might have had the next one right here like this, okay? So what happens is, you can see here now, okay, this triangle, that's fine, but when we go to make this triangle, it jumps over the corner, right? And that's not what we want. That's really bad. That's where that flickering happens. And so if we had another one that went here, okay, this one might be okay, but look at this. Now it's the opposite problem, where instead of jumping over this corner, it doesn't touch that corner, right? And it also didn't get the light down to here, for example. So we have some problems with this method. It initially looked okay, but it's going to cause jittery things and inexact things. So what can we do to solve that? Well, one solution that you might be thinking of is just more and more line segments, right? The more line segments we add, the more accurate this will be. And that is true, right? The more line segments we add, the more accurate it'll be. However, that is going to take a lot longer to compute if we add millions and millions of these things, so we have none of these artifacts. But what is it that we're really trying to do? We are trying to figure out where the light coming out from here intersects with these objects, right? And if you think about it a little bit, you can make this really cool optimization. The only places that it's going to switch from intersecting to not intersecting is at the vertices of these objects, right? So for example, if I shine a ray here, or here, or here, or here, it's still going to be intersecting with this line segment. And the only place that that is going to change is when it goes from here at this vertex to no longer being at that vertex, right? And similarly, it's only going to change once it gets past this vertex over here. So there's that idea of it's only going to be different at the vertices. So why don't we shine the light, or the rays, why don't we cast them at all the vertices? Okay, so now let's look at this. So if we just shine the ray at the vertices, well, okay, this one is going to go like this, but it's going to intersect here, right? This one is going to go to here. This one is going to go here. This one is going to go up here, like this. This one is going to go over here. This one here. This one to here, but it's going to intersect here, so we'll keep it like this. And this way, we're going to do this, all right? So if we do that, then we get the following. So I'll go back to the website. Now, we are doing this, okay? But there's one little extra step, and that extra step is necessary because of the following. If I then make, like for example, I want to keep going with this to show you. So here to here, and here to here. So if I started just doing this, just to the vertices, and then I made my triangles, right? You can see that these triangles don't extend all the way to the bounds of the environment. They sort of stop between the vertices, right? Stopping between the vertices is fine if there is an intersection, like right here, but if this ray should go all the way like this, then this is not what we wanted to do, right? So what we're going to do in order to solve that problem is we're going to shine some extra rays. And those extra rays, so for example, if I shine a ray at a vertice or at a vertex like this, I'm also going to shine one just to the left of it. and I'm going to shine one just to the right of it. Okay, so it'll end up looking something like this. So the one to the left of it won't make much difference, but the one to the right of it will actually go all the way to the edge. And then I'm going to shine one at this one, directly at it. Then I'm going to shine one just to the left. That one's going to go all the way to the edge. And then this one's going to go all the way, or this one is going to intersect here. So now we actually do have this triangle which goes all the way to the edges. So for each ray that we shine at the vertices, we're going to shine one just to the right and just to the left by like a minute amount. And that's going to give us this right here. And so that's what this is doing. If you see here at the edges, like down at the bottom, you can see that it looks like there's a ray going to the vertex and then going past the vertex all the way to the edge. That's the one that was just slightly deviated so that it got past the vertex. Then when we take this and we draw our triangles, we get this. So now we have the really smooth, accurate calculation that we wanted to perform. Okay, so that's how we get to this point. And the video that I showed in the slides was literally me just saying, okay, wherever this is red, that's where the light is shining, and wherever it's not red, that's where the light is not shining. And so what we can do is we can just do this, for example. We can color the areas where it was white, we color that black, and then we color the areas where our rays intersected, that's going to be white. So that's where the light is. And in this example, what they did was they shined a few extra rays and did this cool little shadow technique here. And then they took that and then they added a little texture thing, which it's just a little, if there's instead of drawing the blackness there, they drew a skeleton, right? If it was skeleton, or if it was light, they drew a person. All right, oops, I hit that example. So that is how we took our very simple line segment intersection calculation and made something really cool like this. And this website, if you go through it, it has all the math. It tells you exactly what they did, and you can use this for your final project if you want. Now, you don't have to produce the exact same result, the same quality, the same like, okay, now there's a texture, now there isn't. But I do want there to be some sort of lighting effect for your project, and this is a pretty good one to use. Okay? So that's how we go from the very, very basic math of 2D line segment intersection to some sort of lighting effect.